In my previous video, we looked at the general idea of pipelining, how to stream data from one algorithm to another. In this video, we look at some concrete implementations of this general idea of pipelining. So do not confuse the two. Pipelining is a general idea. Here we look at some implementation options, which are very important in database systems. Those options I'm showing here are widely used, especially in disk-based systems. So we had this graphic already. Here we had a visualization of this pipelining idea for a concrete query plan. And how could we implement that? For that, we first look at a specific interface that's very important here. That's called the operator interface. So the operator interface can be used to implement pipelining. How is that done? Well, let's first look at the methods. We have three methods only in this interface: open, next, and close. And actually the idea is super simple because open and close correspond to what you probably already know in the context of object-oriented programming. Open basically corresponds to what the constructor does. The constructor. Close corresponds to what the destructor does. In Java you do not have this, but in C++ you have that. In C++ the destructor is visualized with this symbol, and then comes the class name. Afterwards, the class name. In Java, so this is C++, let's write it here, C++. In Java, however, you don't have it. So if you look at Java, you have a method called finalize. However, it's not guaranteed that this method is called by the virtual machine, so be careful with that. If you really implement an operator interface in Java, do not just leave away the close method, really call it explicitly, it's really important. I would also consider to keep the open method, even though you could put it into the constructor. If you keep it separately, it has this advantage that you may reopen an operator again. We will see that in a moment what that means. So sometimes it makes sense to be explicit here, even though this could be put into the constructor. So what open does is similar to what a constructor does. It initializes the operator, which may mean it creates a temporary file, it allocates some memory and so forth. And of course, a close method does the inverse. So if you created a temporary file here, you can delete it here again. If you allocated some memory in open, you can free it again here in the close method. So this is performing cleanup work if that is necessary in a specific implementation. However, the important thing is this method here, this next method. This is called by any user of this operator to retrieve the next chunk of data. So any chunk is returned. And chunk here means it's a subset of all of the data we're talking about. So for instance, if the operator runs on individual rows, you would have to call next for each and every row in a table. If this operator returns all the rows of a table, you have to call next for every row of that table once. However, if this is a bigger chunk, say an entire horizontal partition, so if this is a table, let's write it down again. Let's call it relation R. And you have here individual rows. The question is, what is the chunk in this world? So usually many older system designs say every row is considered a chunk. If that is a row here, those are rows, and I have 1, 2, 3, 4, 5, 6 rows, you will be calling next 6 times to retrieve all of the rows of this specific table. However, no one forces you to use an operator in that way. You could also say, no, for me, a chunk is like 3 rows at a time. So you would say this is a group of rows, and that could be a chunk. That could be your definition of a chunk. So it depends on how you want to define this term chunk. Again, in many older designs, many old disk-based systems use this idea of calling next on each and every row, which has pros and cons. We will look at that in the lab and later on in this video what that means. There's a related interface to operator, and you might know that from Java already. That's called the iterator interface. You find it in this package, java.util.Iterator, and looks very similar to the operator interface we had here. However, the iterator interface from Java has some problems. The first is it doesn't have an explicit open method. And it also doesn't have an explicit close method. That's not available in that interface. I just kept it here in the commands to show you the differences and similarities to the operator interface. And what it also has is this this next method, returning a chunk of data. This is specified by a template parameter again, as before. So here, the type that's being returned here is a parameter of this template, or a generic as it is called in Java. Again, depends on your programming language, how you want to call it. But it's the same idea on a high level. So here you return a specific type, and that's specified here. So every next call returns that type. However, there's an additional method. This one here, hasNext. The contract here is that you should call hasNext before calling next. This signals whether there is another element available that you can retrieve from this iterator. So before calling the next method, you should call hasNext. If this returns true, then you are allowed to call next here. That is the contract. And this is good and bad at the same time. It's good because it separates the two aspects to understand whether some element is still available and then actually retrieving the element. However, it has quite some problems because in many situations, in order to determine whether this returns true or false, you have to perform all the work the operator is intended to perform. So a better way might be to do it as the operator is doing it here. Here you see you don't have a separate hasNext method. Here you have to find out separately how to do that. So for instance, you could have the convention to say, whenever this next method returns null, a null pointer, this signals that no more data is available. And then you wouldn't have an extra method performing all of that work like the hasNext method, and you would have all of that in one method call. That's one option for doing that. So I would recommend to go for an interface that only has one method and not this method. So this iterator interface from Java was really designed having different goals in mind. This is a general purpose interface that allows you to iterate over Java collections. It has different goals, so it looks similar, but it has slightly different goals. I'm just mentioning it here because the two interfaces are often confused. And there's another method here, this remove method in java.util.Iterator, which could also be used then to remove elements from the underlying collection. So the contract is, once you called next on this iterator, then you are allowed to call remove as well. And that removes the last element returned from the underlying collection. So that is something we don't really need in databases for the moment. And this is something that's also not present in this operator interface, and we don't really need it. Again, if you implement it in the context of a database system, I would recommend to go for this operator interface, which is much smaller and leaner and does everything we need to do in the context of database systems. Again, back to this picture we had. Now we want to translate this to our pipeline. We want to translate this to operators. And one way of doing that could be the following. We could say each and every algorithm we find here on the left side could be translated that we say every algorithm becomes an operator implementing that operator interface. So for instance, here the index seek operation becomes an operator, the sorting becomes an operator, and so forth. Simple hash join becomes an operator. Even the individual filter operation becomes an operator. That is one way of doing that, and let's call it the textbook way. That's a textbook way. Textbook translation. You will find that in many textbooks. They do it like that. However, it has some problems with respect to performance because this is separate instances in your programming language. If you go back to the operator interface, there will be a special operator implementing this. So if we have a filter operator, it will implement this operator, this general interface. So we will have a class filter implements operator. Okay, and then what will it do? Basically the idea is, if we look in a separate video at that, it will filter out the stuff that does not qualify. So it will only return those tuples qualifying under a specific condition. However, this also means that there will be several function calls. So for each and every tuple that is sent upwards here from this index sequential access method operator, it will be passed to this filter operator. There will be quite some function calls for each and every tuple flowing through this operator. At least the next call will be executed for each and every tuple. And this will lead to quite some overhead in terms of function calls. That is one problem of this approach. So if you really say each tuple is processed by next call, in other words, if you go back, this chunk translates to a row in next call. If you really say a chunk is a row, as visualized also here in this example, then you will have a function call. You will have a next call for each and every row. And that may introduce quite some overhead in terms of function calls. So the bottom line to understand here is this idea of using rows to iterate on is okay. So let's write it down here maybe. So how to translate what is a chunk? Yeah, I think an easy way of phrasing that is to say in a disk-based system, it's often a good idea, disk-based database system, to use rows. In a main memory system or anything with a faster storage device and disks, main memory, DBMS, you need something bigger here. This could be chunks, this could be horizontal partitions. We will even see a case where we pass entire columns or parts of a columns to the next operation. So here you should be careful because the function overhead may be considerable, may be a problem in a real system. There are a couple of other interfaces you should know. There's not only this general operator interface, there's also the result set interface. You may know that from Java. JDBC is doing that, JDBC interfaces. So JDBC is used to connect to a SQL database. You need a driver to connect, and then you can iterate over the data that is being returned. So basically, you should know that from the undergrad lecture, you have this JDBC driver, and then you send a SQL command to the database system through that driver, and then so this sends the result set back. And here again, you can iterate over the results. However, it has slightly different semantics compared to operator and iterator again. So the basic idea is something like that. If you have your interface again, you need to define the granularity you're operating on. So we will see in a moment how that is used in JDBC. JDBC operates on rows. However, again, this does not have to be like that. The general idea works on any granule, on any chunk you may think of. So then you have again open and close methods as in operators. You have a next method. However, this does not return that concrete chunk, the next chunk. It just returns Boolean. And here the contract is similar to the one of hasNext and iterator in a way. So it returns true if we are on a valid pointer position. So basically what you do with this method is you move the pointer forward by one element to the next chunk. Only after moving this pointer forward, you call different methods, you call additional methods to retrieve sub-elements, sub-chunks from that chunk. And that is done here. So in other words, again, assume we have, let's say, we have a couple of chunks. So we have chunk 1, chunk 2, let's name them chunk 1, chunk 2, chunk 3. So when you initialize an implementation of this result set, you first call open once and for all. For every next call, it's just one call to open. Then you call next to position the pointer on the first valid element. Then you are allowed to call these methods. And what they do is, so let's do it here in the context of this example again. Let's say you called next. So when you initialize it, the next pointer is here. You call next once, then it's here. Now you are allowed to call sub-chunks from this chunk. If this is the entire chunk, now you can call a method like this. So get sub-chunk, whatever that means, with a specific key. Yeah? So you need a way to address the subchunks in the chunk. So maybe if you have, let's say, 3 subchunks, and they are enumerated from 1 to 3, you would do something like get subchunk with a key of 3. Yeah? So that will be the call being issued here. So to retrieve this, you would call get subchunk 3, and then you would return that with a specific type that's specified here. Sounds abstract, so let's make it more concrete. This is how this actually implemented in JDBC. So here the chunk is a row. We iterate on rows. Yeah? Every next call moves the pointer forward to the next row. So again, if this is our relation here, this is R. We have a couple of tuples here. We initialize, and once we call it open, we are like here. We're not on a valid position of that table. We call next once, and then the pointer moves forward to the first valid row. And then we typically call a method like that, get string, with a specific attribute index. So of course, here we have attributes. Maybe assume something like this. So here the attributes, let's assume we have attributes starting, I need to have some attribute names here. So those are the labels of those attributes. Let's say they're A, B, C, D, E. If this is the first row, then the numbering starts with 1 in the Java result set. So if you're interested in attribute C, if this is C, you need to call this with a 3. Yeah? So you would be calling getString 3. Yeah? And that would return this specific cell. Of course, this only makes sense if whatever data type you used for C can be returned as a string, can be interpreted as a string. So you have to know the schema in order to do that. This may be pretty expensive in this interface. If you have many rows and many columns, if you call this method for each and every attribute value, this again triggers quite some overhead in terms of function calls. So this is not an interface you will use internally for implementing anything in a database. This is more an interface to the outside world that allows you to connect any database to an outside user, to an outside application. So this is the general idea of a result set if you use rows, but of course you could also use columns. No one forces you to do it differently. This is not how JDBC would do it, but the general idea again is a chunk. So if we say our chunks are columns, why not do it like that? We could say we open this result set, call next once, and then we're on the first column. So again, if we use this idea of a table, let's write it down. We have our table R. We have attributes here from A, B, C, D, E. What does that mean? If we call next, then next points to this column. And now, here we don't specify an attribute index, we rather specify a row index. So in the previous example, if you go back again, here we basically first iterate in this direction and then we pick something from the column list, from the list of available columns. So that is a way of access. It's basically like this, the movement. So if you look at this example, if we iterate over the columns, it's the other way around. We go like this and then we go down. Eventually, we end up with the same result. However, it's just the way how we iterate over this structure. As the overall structure of the relation is two-dimensional, I can make a decision whether I iterate on the rows and then retrieve a specific attribute, as done here, iterate over rows, then get some of the attribute values, or I do it the other way around. I iterate first over the columns, and then I pick a specific value. So here, if I say I want to have row ID, let's assume it's numbered starting with 1 as well as with the columns. If there was only a single next call, and now I get a row ID of 4, I would get 1, 2, 3, 4, I would get this cell here. Yeah, that would be returned. So here's another example. So here we're iterating over pages. Here the chunk is implemented as a page. So basically, you could have a method then that returns you an individual row from that page. Yeah, if you look at the slotted page model we had in the previous video, every page has a specific number of slots. And then if you specify the slot, which is the suffix of the tuple ID, as we learned in the other video, then we can here return a specific row. And again, on that row, we can retrieve a specific attribute. But you could also say get column on that page. Yeah, that would be another way of interpreting that. Again, if we pin down a page here, there are different ways to there are different ways to organize the data on this slotted page. Let's assume this is a slotted page of some sort. So we could have row layout, but it could also be in PAX layout, for instance. Assume we have something like that. Then here we have all the attribute values from attribute A. Here we have all the attribute values from attribute B. Here everything from C. Yeah, so if it were PAX layout, if you're unsure about that, go back to this video. So this would mean that this page contains n tuples. However, internally in the page we have a column layout. So again, you could use here a method call to get the column on that specific page, which would mean you would iterate over those blocks. There would only be 3 next calls pointing to valid data. First time you initialize this, you're here. Then you call next for the first time, and then you're here. Now, if you have a method like get column, and then here's the attribute index, and here we get a column, then this would not return the entire column of the table, but just the column with respect to this page, this column here. That is all the A values of tuples existing on that specific page. So that is how we could use that in the context of PAX. So important for this video is really to understand and make the difference between the concept of iterating over a specific collection, over a specific set, a specific sequence, and the granule used for iterating over the different sources. So again, we have 3 different interfaces we talked about. There's this operator interface that I would really recommend. In many cases, it's a very nice and lean interface and can be used to iterate over arbitrary chunks. A similar interface exists in Java, as we have seen. That's the java.util.Iterator interface, can also be configured to iterate over arbitrary chunks, however has some problems. So I would kind of recommend against it. Do not use this in the context of database systems. The third type of interface, which is similar to what JDBC does, however more general in the sense that the chunk may be anything, not just a row as used in JDBC. So this is a nice interface for iterating and for interfacing with the database system. So it's an interface that's useful for users and an interface we also use for testing in our project. However, for all of these 3 concepts, so let's write it down again, you really have the cross product of all of those. So you have here the operator interface, you have the iterator interface, you have ResultSet-style. Yeah, let's really call it ResultSet-style. It's not this concrete result set of JDBC, which is already bound to a specific granule. So we have this on the one hand, and then on the other hand we have granules. We could have a row, we could have a column, we could have a page, for instance. We could have a horizontal partition, a vertical partition, horizontal partition of the data, a vertical partition. So let's write this down. Then we get a big table like this. And then we get all the options. So it's a cross product of those options, basically. We could use an operator with columns. We could use an operator with vertical partitions, an iterator with pages or with rows. ResultSet-style can be anything again. You can combine it with anything. This is where JDBC sits. This specific combination. This is a JDBC ResultSet-style interface. The operator interface is typically also used. So disk-based operators are typically here. And the same if you used iterators, of course. It's the same stuff here. Also disk-based operators. Okay? However, this space also exists, and you should be aware of that, not to confuse it, because many implementations are row-oriented, many sit here. All of this also exists and should be exploited whenever possible. So let's look at some more concrete implementations. Let's look at more examples. How do we implement operators? That is done in the next video. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there.